Hi and Assalamualaikum. So today our group will be presenting about application of line integral. So this is our group members.
First, we will start with the history of the line integral. The concept of the line integral was developed during the 19th century together with the development of vector calculus. It was introduced to extend ordinary integration to situations where quantities accumulate along a curve instead of a straight line. Early contributions were made by George Green and William Rowan Hamilton, especially in studying work done by force fields. Later, line integrals became very important in physics and engineering applications such as fluid flow, circulation, and work calculation. A line integral is an integration performed along a curve, denoted by C. There are two main types of line integral. The first is scalar line integral, as shown in figure 1. This integral is used to evaluate scalar function along a curve C, where ds represents a small element of arc length. It is commonly used to calculate quantities such as mass or density along a curve. Next, figure 2 shows the line integral in two-dimensional form. This form involves two functions, fxy and gxy, and is evaluated along a curve in the xy plane. Lastly, figure 3 shows the second type of line integral, which is the vector line integral. This integral is used to calculate the work done by a vector field when an object moves along a specific path in three-dimensional space. Therefore, line integrals can be used to measure different quantities along a curve, depending on whether the function is scalar or vector. Lastly, there are the conditions of applicability of the line integrals. A line integral can be applied when the vector field is conservative, continuous, and defined on a simply connected domain. However, it is not applicable when the vector is non-conservative, the domain contains poles or discontinuities, or when no potential function exists. These conditions are important because they determine whether certain theorems, such as the fundamental theorem of line integrals, can be applied to simplify the calculations.
Now, I will present question 1. The question asks us to evaluate the line integral f dot dr, where fxyz equal to x squared I plus 4eyj plus 2zk, and the curve is rt equal to ti plus ln tj plus 3t squared k from t equal to 2 until 3. To solve this question, I use two methods. First, solve it by manually and then verify the answer by using Maple. First, write the parametric equation from the curve. X equal to t, y equal to ln t, z equal to 3t squared. Then, differentiate each variable with respect to t. dx equal to dt, dy equal to 1 over t dt, dz equal to 6t dt. These values will be substituted into the line integral formula. Next, substitute x, y, and z into the vector field. The vector field becomes FRT equal to t squared I plus 4e power of ln tj plus 6t squared k. Since e power of ln t equal to t, the expression simplifies further. Next, calculate the dot product FRT dot R prime t, which gives 3t power of 4 plus 36t power of 3 plus 4. Then, integrate from t equal to 2 to t equal to 3. After evaluating the defined line integral, the final answer is 3578 over 5. This graph shows the parametric curve represented by RT. The curve starts at t equals to 2 and ends at t equals to 3. It helps us visualize the path along which the line integral is evaluated. Now, I will verify the solution using Maple. First, load the required package by typing with vector calculus with plots. This package allows Maple to perform a vector calculation and plot the graph. Next, I define the vector field and the curve. The command is f equal to x squared for exponent y to z. Then I define the curve as r equal to t ln t and 3 power of t squared. Maple successfully displays both the vector field and the parametric curve. After that, I differentiate the curve using dr equal to diff rt. Then I substitute the parametric equation into the vector field using f sub equal to subs x equal to t, y equal to ln t, z equal to 3 multiplied with t squared and f. Now, both expressions are written in terms of t and are ready for the dot product. Next, I calculate the dot product using integrand equal to dot product f sub dr. Maple gives the integrand 3t power of 4 plus 36t power of 3 plus 4, which is exactly the same as the manual calculation. Finally, I evaluate the integral using line integral equal to int integrand t equal to 2.3. The result is 3578 over 5. This confirms that the manual calculation is correct. Finally, this slide shows the three-dimensional graph generated by Maple using the space curve command. The red curve represents the path of the line integral from t equal to 2 to t equal to 3. This graph confirms the curve used throughout the calculation. In conclusion, both the manual calculation and the Maple calculation produce the same answer, which is 3578 over 5. Therefore, the result has been successfully verified.
So now I will presenting the solution for question 2. Question 2 asks to evaluate integration of y dx minus x dy, where c consists of the line from negative 40 to 40 and the semicircle y equal to square root 16 minus x squared from 40 back to negative 40. We will evaluate by two approaches. First, by manual calculation, and second, by using Maple software to verify our results. Before we integrating, we need to understand the part which is labeled as C. The question states that C is made out of two parts. The first part, C1, is a straight line segment, and the second part, C2, is a semicircle. To solve this manually, first we must parameterize both parts. For the line segment C1, since it lies flat on the x-axis, y is simply 0, which also means the differential dy is 0. For the semicircle C2, we can rewrite it as x squared plus y squared equal to 4 squared using trigonometric functions, where the radius r is 4. We parameterize it as x equal to 4 cos t and y equal to 4 sin t. Differentiating x and y give us dx equal to negative 4 sin t dt and dy equal to 4 cos t dt. Now, let's proceed to the integration. The total line integral along C is the sum of the integral C1 and C2. First, let's look at C1. When we substitute y equal to 0 and dy equal to 0 dx into the expression y dx minus x dy, the entire integral becomes 0. Next, for C2, we substitute our triangle parameterization values. This change our integral limits from 0 to pi. Expanding the term gives us integral 0 to pi negative 16 sin square t minus 16 cos square t dt. By factoring out negative 16, we can use triangle identity sin square t plus cos square t equal to 1. This leaves us with a very simple integration constant negative 16 from 0 to pi. Evaluating this integral gives us our final answer is negative 16 pi. To help everyone visualize this better, here is the sketch of our path. As you can see, C1 moved from left to right along the x-axis from negative 4 to 4. Then C2 formed the upper boundary of the semicircle, moving in a counterclockwise direction from 4 back to negative 4. This forms a closed loop, which is vital for calculating our total line integral. Next, we wanted to verify our manual findings using Maple software. To begin our coding script, we first loaded the necessary package by typing with vector calculus and with plots. This allows Maple to recognize vector operation and generate the graph we need. For the line segment C1, we define x1 equal to t and y1 equal to 0. Then we use the diff command to find their derivative. Finally, we integrate the expression from t equal to negative 4 to 4. As expected, Maple gives the output 0, which match our manual calculation. Next, for the semicircle C2, we enter the parametric equations x2 equal to 4 cos t and y2 equal to 4 sin t. We calculate the derivative and integrate from t equal to 0 to pi. Maple gives us negative 16 pi. By adding both integrals together, we get the total value of negative 16 pi, proving our manual working is correct. To visualize the path in Maple, we plot C1 separately first. By using the plot command, with t from negative 4 to 4, Maple displays a straight blue line along the x-axis, representing our first path. Next, we do the same for the semicircle C2. We plot the parametric equations with t from 0 to pi and color it pink. The output clearly shows the curved upper boundary of our region. Finally, we use the display command to combine both plots. We also set the scaling to constraint so the shape is not distorted. This complete graph confirms that our entire path C is modeled accurately. In short, both manual and software methods give the exact same result.